Have you ever stopped to think about how adding something as simple as salt or sugar to water can completely change its behavior? Well, today we're diving into the really cool molecular science behind that. We're going to figure out exactly why a solution acts so differently than just, plain old water.
So to get our heads in the right space, picture this. You've got a puddle of fresh rainwater on the sidewalk, and right next to it, a puddle of seawater. Why does that freshwater puddle seem to disappear so much faster? The answer is hiding in a really neat concept that we're going to break down right now.
All right, so before we can really get into the salt water, we need to understand what's happening with the fresh water first. And it all starts with this idea called vapor pressure, which is basically about the constant escape of molecules from a liquid surface.
So what is vapor pressure really? Well, imagine all the molecules in a glass of water are just buzzing with energy, constantly moving around. The ones right at the surface with enough juice can literally break free and launch into the air, becoming a gas or a vapor. And that push they create as they escape, that right there is vapor pressure. The more molecules that can make that jump, the higher the vapor pressure gets.
Now, in something pure, like our freshwater puddle, it's pretty straightforward. 100% of that surface is made of water molecules. The whole thing is basically one giant, unobstructed launch pad, giving them all the opportunity they need to make a great escape.
Okay, but what happens when we mix things up a bit? This is where it gets really interesting. What happens when we invite a guest into our liquid? A guest that, frankly, has no intention of leaving.
And we call that guest a non-volatile solute. Just think of stuff like sugar or salt. When you dissolve them, they mix in perfectly, right? But they themselves have almost zero desire to turn into a gas. They're happy right where they are, staying put in the liquid.
So what do you think happens when these stay-at-home solute particles meet our escape artist water molecules right at the surface? Well, you get a kind of molecular standoff. And this, right here, is the absolute heart of what we're talking about today.
And here you can see it all in action. Over on the left, that's our pure solvent. All systems go. Every launch pad is open. But now look at the solution on the right. Suddenly, some of that prime surface real estate is taken up by the solute particles. They're essentially acting as little roadblocks, blocking some of the exit routes. With fewer spots to launch from, fewer water molecules can escape, and the direct result, the vapor pressure goes down. It's as simple as that.
Now, here's a really cool twist. You might think the type of roadblock matters, right? Like a big, clunky sugar molecule versus a tiny salt ion. But it turns out, the science doesn't really care about that. It's just a numbers game. Let's just focus on a number for a second. 1 mole. Now, for anyone who needs a quick refresher, a mole is just how chemists count things. It's a huge number, yeah, but you can just think of it like a baker's dozen for molecules. It's just an amount. And here's the key. Get this. If you add 1 mole of sugar to water, the vapor pressure drops by a certain amount. But if you add 1 mole of something totally different, like urea, you get almost the exact same drop. It's not about what the particles are. It's all about how many of them are there clogging up the surface.
So this incredibly predictable relationship between the number of particles and how much the vapor pressure drops, well, it isn't just a weird coincidence. It's actually a fundamental rule in chemistry. And of course, it has a name.
This is Raoult's law. Yeah, I know. It sounds a little dense and formal, but it's just a fancy way of saying what we've already figured out. A solvent's ability to escape is directly tied to how much of the surface is actually available to it. And that availability is measured by something called its mole fraction.
So what's a mole fraction? It's way simpler than it sounds. It's just the proportion of one thing in a mixture. So if 90% of the molecules at the surface are water, its mole fraction is 0.9. Raoult's law just says the vapor pressure will be about 90% of what it would be if the water were totally pure. It's this beautiful, direct relationship. So we've seen that adding these little non-volatile guests creates a molecular obstacle course, and that lowers the vapor pressure. Which leaves us with one final thought to chew on. If just blocking the exit has this effect, what other surprising things might happen? What other fundamental properties do you think are changed by these tiny molecular gatekeepers? That's something to think about. Thanks for tuning in.